So the next speaker is Mario Pecchioli. Mario is responsible for the Control Center software and infrastructure at the European Space Operations Center in Darmstadt, Germany. He is currently looking after the EGSCC, which he will explain shortly, which will be the subject of the presentation. Thank you, Mario.
Thank you for the introduction. Good afternoon, everyone. I guess I need to introduce a bit the subject for you because I'm not for your domain. As you have heard, I work at the European Space Operations Center, so we'll talk about control systems in the space domain, and in particular about the initiative we are having now, which is the so-called European Ground System Common Core, which is shared among a number of stakeholders. I will try to clarify what this is. So in particular, the motivation and the background, it may sound familiar to you, but we have special problems in this area that each organization is developing and maintaining their own implementation of monitoring control systems, which look similar, but they are managed with a completely independent governance life cycle. They own to different people. The various teams prefer one or the other, so there is very poor synergy and cross-fertilizations across the overall community in Europe. There are many existing implementations, but they've been designed for targeting one or the other phase of the life cycle. So there are some which are more adapted to the pre-launch phases, where you are testing your space system. We are validating before the launch, and others which have been designed, this is our case, more targeting to the post-launch operations, which is when you operate your flying spacecraft. And they have, of course, similar features, but they also have distinct features which need to be implemented. Therefore, so far, there was little sharing between these two worlds. And in particular, whenever there is reuse in the direction of across missions. So it's not in the direction of reusing the same system within a given mission from phase A to B, C, D, but rather reusing across missions. So you have general implementations which are customized for a given mission, but always targeting a given phase of your mission. And of course, many of these systems, which you can anticipate is quite a common situation, are experiencing maintainability reasons, problems, because the life cycle of technology is much faster than the life cycle of our systems. So who is involved in this initiative? We have the main stakeholders of Europe in this domain. These are the European Space Agency, which I represent. But there are two centers that are involved from the European Space Agency. This is the Operations Center, located in Germany, and the Technological Center that looks after the space segment pre-launch, located in the Netherlands. Then we have the main primes. These are Airbus Space and Defense, OHB Systems, and Thales Alenia Space. And then we have the main national agencies in Europe. This is the French one, CNES, and the German one, DLR. So we have a very big setup, which is to be managed, of course. And we manage this at the level of steering board and at the level of technical details. So there are two levels, which, of course, contain representatives of each of these stakeholders. And below this, we have implementing contractors. In particular, we are now in the phase CD, so we are developing the system. And these contractors are originating from Europe, of course, so it's a big constellation of companies that collaborate together in a consortium. So what is the rationale for this? The rationale is that we are sharing the same problems, and we would like to find a common solution, which is more easily said than done. We would like, of course, to share the efforts which we need, all of us individually, to modernize what we have. And each of us would not be in the situation today to invest so much to replace the existing systems, because they're quite complex. They have a lot of maturity, and in order to really implement something equivalent, you require a lot of investment. And overall, then in the future, we would like to reduce the overall cost for managing all these infrastructures, also for developing specific systems for each mission, and also the costs which are related to validating these systems across the various phases in a mission. So once you have something which works in phase CD, which is developing a space segment, you do exactly the same effort to validate all the data, all the systems again, when you move to mission operations preparations. And last but not least, we would like to promote cross-fertilization, because once you have what we call a common core, so something which is really representing a common platform to develop, typically you see that also the concepts try to rationalize and harmonize, and all the ancillary implementations which come around become interoperable, become compatible with each other. So you can exchange the implementations as well as the concepts much more easily if you all work around the same kernel. I would skip this because I see that I'm already late. What are the features of pre-launch systems? Why are they different from what we normally do in mission operations? Here, the focus is to make sure that you can effectively validate. So it's like a test system. It's not the same thing for when you're testing the software, when you're using the software. So they're testing the spacecraft, we use the spacecraft. And when they're testing, they need to concentrate on repeatability, on traceability of what they're testing, on the ability to integrate the same system in different scenarios, to interface with it with different equipment. So they have a very complex setup which is put in place in order to simulate the environment and to be able to interface with the various subsystems at various levels of integrations. This is different than what we do when we are in flight, because we have a complete system which cannot change unless we command the configuration changes, and they have a continuously evolving system. And they need to repeat the same test activities in different scenarios. And what they normally want is to have simple systems which don't require a lot of familiarization effort, because the people don't want to spend the little resources they have to familiarize with the system. They just want to invest to test their own systems. We have different situations in the mission operations. We have many users in parallel. It's not unusual that we have 50, 60 users during critical phases. They're all accessing the same system behind. They want to play different roles, but have a consistent view of the system under control. You need to adapt to various types of missions. We have missions which have very short visibility passes and very short propagation delays. This is typical of Earth observation missions. Other missions which have very long passes and very short propagation delays, for example, astronomy missions. And the most difficult case we have is when you have very long passes, but also very long propagation delays, which is, for example, deep space missions. Basically, there is no real possibility to interact in real time with the system under control. And we therefore have also two types of control, basically. We have control in real time, which is probably more what you do normally with your systems, but also what we call offline, which means you're not operating your system interacting in real time, but basically you upload the schedule of things, then you download all the telemetry data which you can receive in the next pass and verify whether commands are being executed properly, reconstruct the state, do fast processing of all this data in order to identify alarm conditions. So it's really different than what the people are used to do in the pre-launch phase. So, of course, when you are doing a new generation system, then you ask yourself whether you would like to emulate the old systems or if you would like rather to rethink them. And in our case, it's more or less a must to rethink them because we have too many that contribute to this. We are trying to develop now a new solution for many systems and not only for one. But when you ask the users who are used to a given system, they normally tend to tell you, I would like to get the same, because the users are always complaining with the systems they have, but at the time when you propose a new one, they start liking what they have. So you can make it more sexy. This is what we tried sometimes to do, at least in the terminology and concepts. You can make it more modern, modular, and you can make it more maintainable. This is the dream of any good software engineer. You can make things which are component-based with standard interfaces, and you can create what you want and maintain it very easily. But I'm sure the people would prefer the original if you propose something like this. So we are trying really to rethink what we have done. And we are trying to find solutions which are common and not just add one solution on the top of the other, which would lead to an extremely complex system which cannot be managed. So what we are doing is basically an onion type of design. We are starting from the kernel and then creating things around this in a way that the more the farther you are from the center, the closer you are to your specific needs and environment. So you're basically creating the situation that the center can be common, but the layers around can be special for the environments which you're using. We are providing an environment for all the phases, which is basically developing the system, validating the system, also preparing the operations, which is what we need to do for a given mission, and setting all the data. We are trying to adapt to all types of systems. I will probably show this more clearly in the next slide. We have selected technologies which are considered by us modern compared to what we are using in the current systems, but we are not trapped into emerging technologies. We are trying to select things which are quite consolidated and promise to remain available for a long time. And we have an architecture which is more centralized than what we have in our systems, where things are largely distributed. We are trying to go more in the direction of something which is scalable but centralized and probably capitalizes on new technologies such as cloud computing if you really need to have very complex processing to serve your mission. So this is a conceptual overview of the various elements which are part of this core. The central element, which really drives all the functions, is what we call the service implementation. This is what we have designed to be the functions available to users to operate the system. And these functions are common, shared by all systems, all phases. And that's where the conceptual work was done. It was basically concentrating on defining how to interact with your system without looking at the details which are related to the external interfaces. So on the right side, you see the control system adapters. And that is where you start becoming depending on which system you are controlling. Which system you are controlling may be standardized, and this is the case for flying spacecraft, but may not be standardized. And this is typically the case for ground equipment or devices, which need to be interfaced based on their own protocol. And then we have, of course, interfaces which isolate the internal details of the implementation and the external service consumer. So this is conceptually always the case in what we are doing in the system. And it is also layered. So we have the top level is, of course, the services. It's basically the key functions which are offered to an operator to operate the system. And you see the EGSCC in the context of a complete application. That's why we call it Common Core. It's not a complete application. CC doesn't stand for Control Center. It's really only the core. It's quite big, so it's really a big endeavor that we are doing. But it is integrated in a lot of other elements which need to be complementing this in order to form fully formed applications. And these are aiming at pre-launch systems, what we call mission control systems for our mission operations, and ground station monitoring control systems. They would all rely on the same core, but of course extend and adapt this implementation. I'm afraid I need to skip this. We have already gone through phase A, phase B, and we are now during phase CD. We are in the middle of development. We expect to finalize the development by the end of 2019. And at the same time, we are integrating the various deliveries which we are receiving in order to have progressive validation, but also progressive development of the elements around, because we cannot wait for the end of the complete implementation before we start doing anything in our environment, because also the effort to integrate this application will be significant. And at ESOC, we are aiming at using this for the first time for the mission control system, the JUICE mission, which will go to Jupiter. And if we don't use this, it means that we would use the old system, which is called SCOS, which has been designed in the 90s, and the JUICE mission will end into around 2035. So we would be basically using the same system for about 40 years, which you can imagine is not an option if you consider how quickly the software technology changed in these last 40 years. Thanks for your attention.